Now let's talk about the limit of a two-input variable function, z equals f of xy. The notation looks much the same. We say the limit as xy approaches ab of f of xy equals L. So it looks much the same, this notation. All right. So what does it mean? Well, informally, it means as x and y domain values of f of xy get closer and closer to AB, then eventually the f of xy values will get closer and closer to L, which would be a height value, of a value on the z-axis, maybe right here. So let's draw the domain of f to get started, to help us understand what this really means and to help make a more rigorous epsilon-delta definition. Let's draw the domain. The domain of f of xy might be the inside of this blob right here. Domain, D for domain. And the point AB, let's say for the sake of argument, actually let me put it right there. Let's say that's the point AB. So that right there is the point AB. Then let's pick an epsilon and make an epsilon interval surrounding L, so that this upper bound or upper endpoint is L plus epsilon, and this lower bound is L minus epsilon. Look familiar? Okay. Then in the more formal definition of limit, we're going to say this. For any epsilon bigger than 0, we should be able to come up with a delta bigger than 0, so that if xy is within delta of AB, f of xy will be within epsilon of L. F of xy will be in this interval, if this limit is to exist, that is. So then, can I create an interval here? No. A delta interval won't work here, but I can create a disk, a delta disk around AB. In other words, I'll surround AB with an open disk of radius delta. So this radius right here is delta. And the idea is going to be that, oh, you pick an x value in here, then, sorry, not an x value, but an xy value in here, then f of xy will be guaranteed to be in here. Will be guaranteed to be within epsilon units of L. So let me say that again to be clear. Given an epsilon bigger than 0, if this limit is to exist, then there should be a delta greater than 0, such that if I pick an xy within this delta disk, within delta units of AB, then f of xy will be within epsilon units of L. That's, again, if this limit is to exist. Now, notice, one other thing you should notice from this picture is xy can approach AB from any direction, from here, from here, from here. So it's no longer the left and right directions. Okay, so here's the big epsilon delta definitional limit, the Calc 3 version that we've been building up to. First of all, let's let our function, let f of xy have domain values arbitrarily close to AB. So the domain values of f of xy, they are values in R2. Think of the xy plane. They are xy values. We're saying we can get x and y as close to AB as we want, even though AB doesn't have to be in the domain of f. Okay, here's the big definition. Let's use the symbolism. The limit as xy approaches AB of f of xy equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that the distance between f of xy and L is less than epsilon whenever the distance between xy and AB is less than delta but bigger than 0. The way we have to write that is like this. 0 is less than, okay, the square root of x minus a squared plus y minus b squared. Okay, that's the distance formula for points in the plane, right? And we're saying that has got to be between 0 and delta. Okay, so the reason why the distance formulas look different is this distance between f of xy and L, that's the distance between two scalar quantities, two numbers perhaps. And this distance is the distance between 2 points in R2. Just remember what this definition is trying to convey. All we're saying is this: if you give me an epsilon, then I can find a delta such that I pick xy within delta units of AB, then f of xy is going to be within epsilon units of L. In other words, the closer xy gets to AB, then at least eventually the closer f of xy is going to start getting to L, assuming that L exists, that is.